Good morning, everyone. On behalf of the organizers, I welcome you to the Institute of Mathematical Sciences and in Chennai. We would like to thank the speakers for accepting our invitation, and thanks to the participants for joining us here. We are here to remember Professor Amol Kumar Raychaudhuri. Many of us here are not that lucky to be taught by AKR, the brilliant physicist and an exceptional teacher. However, some of us got some essence of his teaching and research from his students and colleagues. And we are fortunate to have some of them as speakers in this conference. We look forward to learning about AKR, his research, and his teaching in this mini conference. At the same time, we will listen to the recent research works on areas related to gravitation and cosmology. Let me introduce you to my colleagues and the organizers of this conference, Professor Manjari Bagchi, Professor Arnav Pal, and Professor V. Ravindran here. You can reach out to any of us if you have any problems during your stay. We hope you will have a nice time at the conference and have a great stay with us at IMSC. Now I would like to request our director, Professor Ravindran, to say a few words about IMSC and this conference.
Good morning, everybody. Let me first welcome all of you to IMSC. Many of you might have already visited IMSC in the past. I can see a lot of familiar faces, also my teachers here. So I'm really proud to have such a meeting at IMSC to celebrate the great man of our physics community who lived, I think, during my early career of my physics. I have heard quite a lot about him, actually. So I'm really happy that we can organize this meeting at IMSC. It started like the following. We were actually walking towards canteen for food. Myself, Manjari and Arnab. Arnab I met actually in the canteen, Dheeraj. And we were talking about somebody organizing a meeting on Professor Raychaudhuri. So we immediately decided that we should have one. Otherwise, we'll be, kind of not of, this is not something that IMSC would actually like to have, So we decided immediately that we should have it actually. While having food, and Arnab, we suggested to Arnab that, we should have a meeting of this kind. So he enthusiastically agreed. Arnab is one of those who is, as you can see, one of the enthusiasts in the meeting actually. So we were really happy that, we could actually quickly decide and take it forward and, get you all here. And I'm really thankful to Dheeraj, Manjari and Arnab for really, putting a lot of effort to get it happen in a very short time actually. So this is very important actually for us also because as he said, rightly said actually, he is an inspirational figure. Not only to those who listen to him, also to those who listen to those who actually heard, physics from him. Because I know many of my teachers also were, students of AKR. AKR is, is known to many of us through his equation, which actually, led to important, ingredients to, the famous Penrose-Hawking, singularity theorem and things like that when it was approved. So it was really an honor to have such a meeting at IMSC. For those who are first timers in the institute, IMSC is an institute where we have 4 groups, physics, mathematics, computer science, and computational biology. Computational biology is the youngest group. It started almost a decade back. And most of us do theoretical physics. And this is our campus. You are staying in the other side of the institute, which is the guest house or hostel come guest house. It's a small institute, but we do very rich mathematics and science. Okay, so I'm happy that you are all here. Not only, you spend time inside, you also spend a little bit of your time going around the institute and also visit some important places in Chennai. There are a lot of things lined up actually for next 3 days. 2 days will be technical talks, and then the last day will be on with children from nearby schools and colleges who are going to come and listen to some of you about AKR, the great man. And it's really, I'm also looking forward to hear more about A.K. Raychaudhuri, because he is one of our, my inspiration actually to learn, physics. So it's going to be an exciting week. And I wish all of you a very happy stay here and enjoy Tamil cuisine. Hopefully you'll like it. Have a nice time here. Thank you.
And a very good morning, friends. So we are all here to commemorate the centenary of Amol Kumar Raychaudhuri, our beloved AKR. So I was fortunate to be one of his students from my undergraduate days. Perhaps I am not very sure about Professor Mani, who is here, when he met him, but perhaps I have the longest interaction with him right from 1975. So this session, we have 3 speakers, and rightly so, the first speaker will be Sayan, Professor Sayan Kar, who did a lot of work on Raychaudhuri equation itself. So the talks are all of 1 hour duration, and I would request the speakers to restrict in 50 minutes so that 10 minutes can be devoted to question and answers, if any. So, yeah, the first speaker is Sayan Kar. Over to Sayan.
Thank you for inviting me to give this talk. I remember that the first time I gave a talk here was in 1996, and Sham was one of the organizers of that meeting. Parth was also there. It was an IAGRG meeting, and of course, IAGRG owes a lot. In fact, it was founded by AKR and Vaidya. All of us know that. So this talk, which I will give you, is actually an old talk in the sense that it was delivered sometime back in an IAGRG meeting. And the organizers actually, I gave them the option that I could speak about something else. And I was told that since it's the first talk, maybe we should remember the life and work of AKR in this conference. And so that is the content of this talk. I would review his life, his work, and also the Raychaudhuri equation. And you can see a title which is a little strange. It says the Raychaudhuri effect. And we normally don't hear about this phrase. So this phrase is actually picked up from a very famous paper of 1970 by Hawking and Penrose, where they use this phrase to describe what is called as geodesic focusing. Okay, I will show you later on where exactly they used it. But somehow the Raychaudhuri equation stuck on, but nobody uses the Raychaudhuri effect. So in a sense, I'm trying to popularize this. So let us call geodesic focusing as the Raychaudhuri effect. Okay, so Raychaudhuri is, of course, 100 years old, 100 plus now. And the number of people who would have met or have seen him will gradually become less and less as the days go by. Fortunately, I had the opportunity of meeting him and seeing him in roughly the last 11, 12 years of his life. It's not that I was a student or anything, but I did have the opportunity of discussing and meeting him and listening to him, of course. And I'm tempted to tell you a little story. Normally, I do not tell such stories, but since it's a small audience and it's all friends, when I joined IIT Kharagpur, and we had a head of the department who was AKR's student, and AKR was some kind of a board of studies member or something like that. And so our head of the department invited AKR to tell us about teaching. So AKR used to come, and throughout the time he was there, his son is actually a faculty in mechanical engineering. So he came to our department. He used to come quite a few times. I have seen him come for various meetings and so on. So he came to the department, and we had just joined. And he was told that you should tell these young people how to teach. But he is not someone who will give sermons or anything. So what he did was, he told us about his experiences. And I remember one story that he said. So he was teaching classical mechanics in Calcutta, in Presidency College. And it was a hot summer afternoon. And he was teaching rigid body dynamics. And he noticed after a while, he had all these equations on the board, and it was very messy and all. So he noticed after a while that most of the students were not listening. And it was very hot, and some of them in the back bench were sleeping, and there was nobody was really concentrating. So what did he do? So he suddenly turned to the students and said, "Why don't you look up?" And up there was one of those famous Calcutta fans which was going round and round. And he said, "Can you tell me what is the moment of inertia of the fan? Can you calculate it?" And immediately the class, they realized that what was written on the board was actually something connected to reality. Okay, so this was one instruction he gave us, that when you teach in a class, you would better try to connect. Because physics is supposed to be about what is happening around us. And this is what I learned from that day. Okay. So that is the AKR story that I wanted to tell you. There are some other stories which I can discuss later on. So let's get into the talk. So what I'll do first is tell you about his life and work. And this is mostly from Diaries of 2002, which has been published by his daughter, Parangama, and of course, Narayan Banerjee also. This is a book in Bengali, which is not really available as such, but those of you who can read Bengali will enjoy going through the diaries. Okay. And there is an autobiography which he had written in these diaries, from where I have taken some of this information. There's also a biography by Jayant Narlikar, which was published in the INSA yearbook or something. Okay, that is also very nice, very well written as such. Okay, so let us begin. So AKR was born in a place called Borishal, which is now in Bangladesh, on September 14, 1923. So he is just about 100 plus. His family used to live in Borishal, and then they came over to Calcutta. So his school education was in Brojamohan Vidyalaya, which is in Borishal. Borishal is, of course, famous for many famous Bengali, including the famous Bengali poet Jibanananda Das. So he had his school education, initial school education in Brojamohan Vidyalaya, and then in Calcutta, he studied in Tirthopati Institution and Hindu schools. So he doesn't mention much about childhood influences, except his father, who was a mathematics teacher, and his father's cousin, Professor Hemchandra Raychaudhuri, who was a Carmichael professor of history in Calcutta University. And he had two brothers of his mother who had brilliant careers in law and medicine. He writes extensively in his diaries about a bout of malignant malaria which he had when he was young in his childhood, and he was seriously ill for a while. And there's a nice story in that book where he says that there was a certain British doctor who came to see him, Dr. Hodge. And Dr. Hodge, after diagnosing his illness, said that he had a peculiar heart. And then Dr. Hodge actually wanted to do research on his heart, but his parents did not allow that. And AKR writes that, okay, when he wrote the diaries, he was 80 plus. So he had lived all those 80 years. So he had his UG and PG studies in physics, which is completed in 1944 at Presidency College in Calcutta University. And then after completing his studies, he initially wanted to study mathematics, but then his parents, his father essentially told him that you study physics, that is better. So he joined as a research assistant, a research scholar at IACS, Kolkata, from 1944 in a CSIR metal alloy project under a very famous chemist, Professor Kedareshwar Banerjee. And he was supposed to work on setting up an X-ray tube, which he writes about extensively. It was called the demountable Hadding tube. Well, he worked on this for 4 years, and he did a lot of things, but he couldn't make that X-ray tube work. So it did not work. So it was unsuccessful work for 4 years. And then the CSIR people came, they inspected what has been done, and they discontinued the project. So he lost his job. And he writes in his diaries that Professor Banerjee, when he met him after he lost his job, Professor Banerjee regretted and said that good work could not be done, but he also said that I know one day you will do good work. And AKR, of course, writes in his diaries that whether it was a sympathetic statement or whether it was actually something which he believed in, but still, despite everything, he was sort of encouraged by these statements. So after that, this was in 1948, and then he joined Ashutosh College in 1949 in a temporary position, and it was at this time that he came in contact with Professor Nikhil Ranjan Sen. And he began interacting and attending the weekly seminars of Professor N.R. Sen. N.R. Sen was actually the only person in Calcutta at that time who had worked in relativity, and he had worked in Germany. In fact, N.R. Sen is the first Indian to write a paper on general relativity in 1924. That will also be 100 years next year. And this paper is very famous. This is the paper on the junction conditions. It was written from Germany. And you must have heard about the Sen-Israel Lanczos-Barabas junction conditions. That paper is the beginning of the junction condition work. Okay, but AKR, of course, didn't like the discussions at N.R. Sen's seminars. So he writes that he eventually distances himself from this group, and because he finds the approach and topics discussed not too much of his liking. However, he retains a respect and gratitude towards Professor Sen. So he had a temporary job in Ashutosh College, and he was still looking for a job as such. So there was an advertisement again in IACS, and he joined as a research officer now in the theoretical physics department in IACS in September 1952. And for job confirmation 1 year later, he was asked to present his work, and the date of presentation, he writes, was 14 September 1953, his birthday. And he gave that presentation in front of the director and the head of the department in IACS. The director was Professor Meghnad Saha, and the head of the department was Professor Devidas Rai. And unfortunately, nothing was conveyed. Most likely he spoke about the work on the Raychaudhuri equation, although he doesn't write about it. So what did these people tell him? They told him that whatever you have done is fine, but it's better you start working on quantum chemistry with Professor Priyodaranjan Rai, who was a nice person. So he went to Professor Priyodaranjan Rai, and Professor Rai gave him some books, and he spent a lot of time reading about chemistry as such. But he himself found a paper by Coulson which was interesting, which interested him, and he started work on network approximation in metals. And he writes and publishes a paper on Coulson's work in 1955. And Coulson later on acknowledges and appreciates this paper in a following paper. And Professor Priyodaranjan Rai also appreciates his work. And at the same time, he also submits the Raychaudhuri equation paper on December 28, 1953. And as all of you know, it was published about 1.5 years later. But before these papers, he actually wrote 2 short comments in Physrev and Bulletin of Calcutta Mathematical Society, and 3 full papers. And this paper in Bulletin of CMS was communicated by Professor N.R. Sen. And here also there is a nice story, because he writes that when he went with the paper to Professor N.R. Sen, the Professor N.R. Sen actually looked at the paper and he removed a large portion of that paper. And the advice he gave AKR was, the more you write, the more mistakes you make. Okay, so therefore you write less. So the 1955 paper, after it was published, that's the famous paper. 2 years later, he receives a letter from Ratanlal Brahmachari, who was a student of S.N. Bose, who was in Hamburg at that time. And later on, he became a famous tiger expert. So Ratanlal Brahmachari wrote a letter to him saying that his 1955 paper has been discussed in the so-called Pascual-Jordan seminars in Hamburg by Otto Heckmann and Engelbert Schuking. So this actually gave him a lot of inspiration, and he submitted a DSc thesis to Calcutta University. And in 1961, the DSc thesis was accepted. The examiner was Professor John Archibald Wheeler, and who was very appreciative of the work. In fact, he wrote that it should be given a distinction. So Professor Kedareshwar Banerjee was the director at that time in IACS, and Professor Banerjee told him that now I will use this DSc report and get a promotion for you. So AKR applies to IACS, and Professor Banerjee recommends his promotion, but it has to go through the IACS faculty, and the IACS faculty opposes his promotion, and he is denied. So after this, in 1961, he leaves IACS and joins Presidency College, Calcutta in 1961. And he continues as professor there till 1988. And as all of you know, he was a renowned teacher, inspiring generations of students at Presidency and elsewhere. After his retirement, he was associated with the Relativity and Cosmology Center at Jadavpur University, and he was also an honorary fellow at Ayuka, Pune, and he passed away on June 18, 2005. So that is a very brief biography, mostly focusing on the initial part of his life. And I guess the part in Presidency College will probably be discussed by other people like Professor Palash Pal, who will give a talk, I think, day after tomorrow. So let me now turn to his research and teaching. And let me show you the papers that he wrote. Since it's not a very large number, so I can actually show what actually he did. So if you see this first page, these are his research papers. These 15 papers are from 1951 to 1961. The light red papers are the papers on general relativity. And every paper, in fact, I have seen all of these papers. In the first paper, which is just half page, he has a sentence, negative mass Schwarzschild solution. Okay. Then in the paper number 4, this paper number 4 is basically a re-derivation, it's in German, it's a re-derivation of the Vaidya solution. Okay. Paper number 5 uses the so-called Einstein cluster. It's a paper on the Einstein cluster. Okay. Then you can see there are a couple of papers. The black papers are essentially the ones on cosmology. So those papers, the second one, the third one, then the 8th, 10th, 12th, and 15th, these are papers on cosmology, but not on the Raychaudhuri equation. And the deep red ones are the two famous papers which deal with the Raychaudhuri equation. And the light blue papers are on quantum chemistry and band structure. And there's one dark blue paper which is on Einstein-Maxwell theory. So you see there's a huge variety of his work in his first 10 years. All these papers are written by him and only him. So these are all single authored papers. These are the first 10 years of his life, of his research career. And by all standards, even by today's standards, this is remarkable. Then after that, this is the time when he joins Presidency College. And you see that he shifts his focus to Einstein-Maxwell theory. The blue papers are essentially papers on Einstein-Maxwell theory. And except the first paper, which is also on the Einstein cluster, the remaining, there are some papers on cosmology, but you can see the appearance of co-authors from here. Most of them are his PhD students. Okay. So there are some interesting, like this paper on tachyons and gravitation is essentially a paper which deals with space-like geodesics. Okay. And there are lots of papers on charged dust, which was something he worked on extensively. So this is up to 1975, and then there was a phase where he went into alternative theories of gravity, like Einstein-Cartan theory, then Brandstich theory, and so on. He also did some work on astrophysics, Faraday's theorem in non-flat spacetime. He was particularly fond of the Gödel spacetime, right from his early days. And he continued work on Einstein-Maxwell theory. There's another interesting paper which talks about temperature-dependent gravitational constant and black hole physics. And then this is the last phase, from 1985 to about 2004. You can see that he worked a lot on current topics like domain walls, then cosmic strings, cosmological models, and entropy. And he came back to the Raychaudhuri equation right at the end of his career, where he worked again on singularity theorems and things like that. And he wrote 4 papers between the period 1998 to 2004. Okay. So this is the entire list of papers that he worked on. What I kind of reading many of these papers, I realized that most of these papers are very precise and very dense, in the sense that he doesn't really write extensively. What you mean by saying writing in full detail, all steps and all that. So the papers are very dense, very precise, not very long as such, but not very hard to read also. So it's a very unique way of writing papers as such. So he wrote a few books as well, like the book on cosmology, which is very famous, his course of lectures on classical mechanics, which is also extensively used by students. This is courtesy Palash Pal and Sumit Das, who actually took the notes and wrote. This third book has been recently republished on electromagnetic fields, and this is now available on the internet. All the chapters are there, freely available to those who have Springer access. And he also wrote a book in Bengali on mechanics, and these two are proceedings. So this is roughly his research career as such. Let me just mention the broad areas he worked on. One was relativistic cosmology, singularity theorems, that was his primary focus. Einstein-Maxwell theory is another area in which he extensively worked. Alternate theories, Einstein-Cartan, Brunstick, C-field, domain walls and cosmic strings, and general results in GR, astrophysics, theorems, comments, etc., and 3 papers in solid state and quantum chemistry, including one on band structure calculation. In fact, I read the band structure calculation paper, and it's actually very nice. When you can take a look at it, despite being something completely different from what he worked on, this paper is also very well written and nicely written as such. So these were the people who worked with him, his PhD students and collaborators. Murari Mohan Shom, who went off to Brazil later on. Sri Ranjan Banerjee was in Bardhaman University. There were 2 people who did DSc under him, Utpal Kumar De and Nikhilendu Bandopadhyay. Ashit Banerjee was, of course, in Jadavpur University. Bidyut Datta, Ajit Datta, S.R. Maiti, and the others. Okay. The only person who managed to write a paper with him who was a faculty was Naresh Tadich, right at the end of his career in 2000. Nobody, all his other papers are with his PhD students. Okay. Okay, so let me now move on to the Raychaudhuri equation, which is the famous paper, and this is the paper where the term was introduced. To the paper by Otto Heckmann and Engelbert Schucking in Gravitation and Introduction to Current Research. And this is what it says: an important theorem for arbitrary models with incoherent matter has been discovered by A.K. Raychaudhuri in 1955. It rests on the Raychaudhuri equation for the scalar of the expansion. So this is where it was first mentioned. And I give this information courtesy Jürgen Ehlers. It is there in Ehlers' tribute to AKR. Okay, so let me tell you what this paper is about. And let me first discuss the original Raychaudhuri way of arriving at the Raychaudhuri equation, which is different from what you read in textbooks. Okay. So this has been retold by Edward Witten very recently in 2020. So you start with d equal to d plus 1 dimensions, space-time M with initial value surface S with local coordinates x. You have time-like geodesics orthogonal to S, coordinate system in a neighborhood of S, and you take point P on the time-like geodesic, which meets S orthogonally at x. The proper time from S to P is t, and you assign P with coordinates tx if P is to the future, or minus tx if to the past. Okay, so this is basically sort of foliation that you're talking about, nothing else. So this is the line element which is assumed, and you can have a G0 I term also, G0 I dxi dt. And Witten, of course, does not include that, but in AKR's paper, that term is included. So if you write the T geodesic equation, it is solved for t equal to tau and xi equal to constant. Then comes the really strange thing. AKR rewrites RTT. This is the main thing in the paper. The Raychaudhuri equation, according to AKR, is written as a decomposition of RTT, nothing else. And it's unimaginable that somebody could write something like this, finally arrive at the Raychaudhuri equation in this way. So he writes RTT, and he breaks RTT up in this fashion. Okay, the second line over here. This is not working, I think. Okay. So this is how he breaks it up. This is the notation which Witten has introduced, G inverse G dot, trace and all that. And then you define a V, which is root det G. G, remember, is the spatial metric. Okay. And then you write theta as V dot by V, which is half trace G inverse G dot. And AKR defines something called sigma ij. He doesn't really call it a shear in his paper. He calls it shear later on. Okay. He in fact calls it phi. The notation used is phi square. So you define this and you just substitute that back in this. That's all. You define a T mu nu in this fashion, and then you write RTT equal to 8 pi GTT. If you use this in this expression for RTT, you will get the Raychaudhuri equation. This is Raychaudhuri's derivation. He starts from RTT and he's able to decompose RTT in this unique fashion and arrive at the equation. And he uses this Einstein equation, which, as we'll see, is not really necessary. Okay. And Witten, of course, gives a name to this equation, RTT equal to h pi gtt. He calls it the Einstein-Raychaudhuri equation. Okay, so this is the derivation, and you can include rotation omega ij if you just put in a g0i term in the metric. That is going to give you the equation with the rotation term. And this V dot by V is what is called the expansion. And my guess is that because he did it in this very strange way, people really didn't understand what he was doing at that time. Okay. In fact, in the 1957 paper, which was published in Zeitschrift für Astrophysics, he actually does it in the normal way which we learn about it today, okay, using the gradient of the velocity field. Okay. Okay. In 1957, in his paper, he also derives it from the Euler equation. And I'll give you a one-dimensional example, which is absolutely one line, nothing else. You have del u del t plus u del u del x equal to f. You construct del del t plus u del del x of the gradient of the velocity, del u del x. And you use this first equation, and you'll get this equation, which is your Raychaudhuri equation. Absolutely straightforward, nothing much to do. 2 lines of calculations, and you'll arrive at the Raychaudhuri equation, simple one-dimensional Raychaudhuri equation. And this, of course, can be generalized to higher dimensions, to curved spaces, and so on and so forth. It's been written in the famous paper of Ehlers of 1961, and Thomas Buchert also talks about it in 2017. In fact, the Ehlers paper of 1961 was not translated till 1996. Ehler didn't allow a translation because he always thought that the credit should go to Raychaudhuri. Okay. So it was finally translated and published by George Ellis in 1996. It's a beautiful paper, very long, very extensive, but it remained in German for more than 30 years. Okay, interestingly, if you look at AKR's papers where he cites the Raychaudhuri equation, you will find very, very few citations of his own paper. In fact, always he would cite Jürgen Eller's. Okay, the other more general route which we learn in our GR textbooks is, of course, the following. You take a curved spacetime, Riemannian, pseudo-Riemannian, Lorentzian. You take freely falling trajectories, which are geodesics. You look at congruences. And this is the definition of a congruence. Through each point in a region, open set in spacetime, one and only one curve passes. The breakdown of definition happens when the curves meet and they pass through, and the curves are geodesics, then geodesic congruence. You assume time-like curves, and that's a picture of the flow lines. You look at the trajectory equation, and then you look at the evolution of del J ui. This is the gradient of the velocity, and you calculate this quantity, uk del k bij. Keeping in mind this relation, which is the non-commutation of the covariant derivative, which gives you the Riemann tensor. So if you just evaluate this uk del k bij, remembering this, then you will end up with this relationship. And this is the equation for the bij. And if you take ui bij equal to 0, because del j ui is equal to 0, you will notice from here, using the projection tensor and the split of bij into the symmetric traceless, the antisymmetric, and the trace parts, you will end up with the final equation for bij in this form. And this has got a term which is del j ai, which is the acceleration term. So from here, you can extract the evolution equations for theta, sigma ij, and omega ij, and these are the Raychaudhuri equations, and these are also the Eller's geometric identities. Okay? So if you take the gij trace of this equation, then you end up with the equation that Raychaudhuri derived, which is the famous Raychaudhuri equation. Okay? So this derivation starts out with the gradient of the velocity field, and you calculate uk del k of the gradient of the velocity field, use the non-commutation of the covariant derivative, and that is all to it. The rest follows. Okay, so sometimes these are referred to as Raychaudhuri equations with an S, because of the fact that you have an equation for the rotation, you have an equation for the shear, and you have a whole set of equations or identities which you can write down. Okay, so that's the reason why that entire system of equations you could call as the Raychaudhuri equations. Okay, so I'm not getting into the details of this. The important point over here is that the omega equation has omega ij equal to 0 as a solution, but the sigma equation does not have sigma ij equal to 0 as a solution in general. Okay, the crucial points are the following. The first statement is there is no general relativity in the derivation of the Raychaudhuri equation. Okay. The Raychaudhuri equations are broader in scope and generality, and they are identities. They are always true. They are, of course, used in general relativity, and we will see how. The two main statements are the following. The Raychaudhuri identities or the equations, whatever you call it, will exist even if there is no theory of gravity. And wherever there is a vector field, there will be Raychaudhuri equation. In a broader sense, the equations are essentially a generalizations of Newton's laws for a collection of particles or a congruence. Okay, and if you want, I can elaborate on this later on. Okay. Okay, so let me now go to the Raychaudhuri effect. So this is the paper where it is called the Raychaudhuri effect by Hawking and Penrose in Proceedings of the Royal Society, London. They write that the fact that they do is essentially a consequence of the Raychaudhuri effect. So what is the Raychaudhuri effect? Raychaudhuri effect is essentially what we normally call as the focusing theorem. And the statement of this theorem is, if the time-like convergence condition holds, which is which is Rij ui uj greater than equal to 0 and omega square equal to 0, initially converging geodesics, that is with a negative expansion, they must focus, which means theta would go to minus infinity, within a finite value of the affine parameter tau. That's the statement of the focusing theorem. The crucial point is the finite value of the affine parameter. If theta naught is negative, then theta will go to minus infinity. That essentially means that these trajectories are going to converge and meet at a point. So there are various ways of proving this, and let me give you one way. You can integrate the inequality assuming convergence conditions, or you can go to the linear second order equation. So let me do it in the first way. You look at the Raychaudhuri equation, and you notice that if you take this greater than equal to 0 and omega equal to 0, then you get an inequality. Now if you integrate this inequality from tau equal to tau naught to tau equal to tau 1, you get something like this, which you turn around to write in this fashion, and you plot 1 over theta versus tau, and you get a straight line. Okay. So the region of validity is here in this shaded region. The inequality is valid in this region, which means that if you're going to start out with a negative value of theta, remember this is 1 over theta versus tau. So if you start out from somewhere here, you're going to hit the axis. When you hit the axis, theta goes to negative infinity. That is the focusing theorem. Okay. So the shaded region is where the values of 1 by theta will lie, provided we start off at tau naught at minus mod theta naught. And it is clear that theta may tend to negative infinity within a finite value of the parameter tau because of the nature of the inequality. So if you have a converging congruence, we'll eventually focus within a finite value of the parameter, and this is geodesic focusing. So it starts out at tau equal to tau naught, then it will diverge to minus infinity at tau equal to tau naught plus 3 by mod theta naught. Now, Frank Tipler in 1977-78 actually showed us that you could prove this using the zeros of a second order differential equation. So you write theta equal to 3 by f df dt, and you get this equation, which is the equation that is advertised in your poster of the conference. Okay. That's the second order equation. Raychaudhuri used G, so G double dot by G. Okay. The quantity in brackets in the second term is a function of tau, and therefore theta will have a divergence, positive or negative, at finite tau if f has a 0 there. So you have to look for the existence of zeros in this differential equation, and what is used is differential equation theory, the Sturm comparison theorems. Using them, you can show that zeros will exist provided this quantity in brackets is positive definite. Okay, so that's the convergence condition, R mk um mk greater than equal to 0. And now if we use Einstein equation like Raychaudhuri originally did in his derivation, then comes the notion of what are called the energy conditions, the various kinds of energy conditions. Okay. And these were actually introduced by Hawking and Penrose. And using those energy conditions, you can translate the condition, the geometric condition, into a condition on matter. And energy conditions are essentially statements of the simple fact that the energy density of matter is positive definite in all frames of reference. Okay. So, in other words, the cause for geodesic focusing is just the attractive nature of the gravitational force. If you include the fact that you are using general relativity, and a null geodesic generalization was worked out of the Raychaudhuri equation by Rainer Sachs in 1961. And the null case can also be obtained in the Raychaudhuri way using a decomposition of RUU, not RTT. Okay? And it is this focusing which Hawking and Penrose called the Raychaudhuri effect, and we should also call it the Raychaudhuri effect. Okay, so there is a singularity theorem, and let me just mention the singularity theorem. And this is called the Raychaudhuri-Komar singularity theorem, which is also there in Raychaudhuri's paper. So if you assume lambda equal to 0 and a perfect fluid energy momentum tensor whose velocity vector u mu is geodesic and irrotational, if the expansion is positive or negative at an instant of time and the convergence condition holds, then the energy density of the fluid diverges in the finite past along every integral curve of u. This is stated as the Raychaudhuri-Komar theorem. And Jose Senovilla in 2014, while reviewing Penrose's singularity theorem, made a statement which is very important. He says that this theorem, the Raychaudhuri-Komar theorem, has one virtue that will be lost in the more advanced singularity theorems. It predicts that the singularity means a divergence of the energy density, and it says where to locate it. This fact is not there in the latest singularity theorems. Okay, yeah. So the 1965 Penrose theorems introduces trapped surfaces, which also is defined using the expansion. Okay, so let me now come to the fact that the Raychaudhuri equation is something which is universal and ubiquitous. And I'll give you 4 recent examples. I will show you the work that has been done by various people in recent times. And the first one is something completely different, in a completely different field, water waves and tsunamis. See, Michael Berry in 2007 wrote a paper where he had this figure. This figure is taken from Michael's paper, where you can see a slight undulation over here, right? So there's an island, okay? And there are water waves going on top of that island. And you can analyze the behavior of the water waves, and you will see there is a chance of a caustic formation, okay? And the caustics essentially are calculated using higher order stationarity, which means the second derivative is equal to 0, okay? Now, last year, these people, Theo Torre, Max Lloyd, Sam Dolan, and Silke Weinfurtner, they wrote a paper where they showed that you can generate those caustics by tracking down the locus of points where the expansion diverges to negative infinity. And they essentially used analog gravity metric and the geodesics in that analog gravity metric, and they used the Raychaudhuri equation. And we also tried to do this. We calculated it, ran the numerical things, and we got the same answers. So it is something that can really be done. Okay. So this is one example. The other example is in 2017, where if you look at the behavior of a laser spot as it moves through a dielectric, what is the behavior? What is the change in shape because of the nature of the dielectric? And this also can be done. This can be analyzed, analysis and tracing of congruences of light through media, and the kinematics of the Raychaudhuri equation can be used to understand the nature of the behavior of the shape of the laser spot. And this is worked out in this 2017 paper by these people. The third one is in mathematics by a famous mathematician, Michael Friedman, and it's called the Bishop-Gromov theorem, where the Bishop-Gromov theorem upper bounds the rate of growth of volume of geodesic balls in a space. So here you're using something opposite to focusing. You're trying to see about the divergence of a family of geodesics, and you're trying to bound the rate of growth. And this apparently you have got a bound for inhomogeneous spaces. That is important in this paper. And this proof makes use extensively of the Raychaudhuri equation. The Michael Friedman's, this paper and the next paper, which he has written later on, where they have used or found a enhanced Bishop-Bromo bound for spaces which are inhomogeneous in nature. Okay. And finally, let me tell you about another paper, which is Gravity from Thermodynamics. And the reason why I'm telling you about this is not so much about gravity from thermodynamics, but the fact that in the appendix of this paper, there is an appendix called Raychaudhuri and Bochner. Okay. And Salomon Bochner was an American mathematician. And in 1944, he wrote a paper called Curvature and Vector Fields, where he wrote this identity, which is known in mathematics as the Bochner identity. And these people have tried to show that if you take the omega ij equal to 0 Raychaudhuri equation for normalized velocity fields, you can derive this from this Bochner identity. This is not to say that Bochner did the Raychaudhuri equation earlier, but it's a fact, and it's good and important to know that you have something in mathematics which actually relates to the Raychaudhuri equation. Okay, so these are a few things, and these are the other areas: gravitational lensing, gravity thermodynamics, mechanical system, elasticity, RG flows, strings and membranes, quantum Raychaudhuri equation. One of your former students of IMSC, Shaurya Das, had done some work on this. Large-bar Raychaudhuri equation, Larry Ford and others did some work. Jamming phase transition, Partha Majumdar has some ideas on that. And there are many more, and including if you look even in the last 1 month in the archive, you will find several papers which actually apply the Raychaudhuri equation in various contexts. I just want to mention another work of Raychaudhuri, which is called the Shom-Raychaudhuri spacetime, which is the cylindrically symmetric charge dust distribution in rigid rotation in general relativity. This is also quite well known, by the way. And this is the metric. It has 0 net Lorentz force, electrostatic field, axial magnetic field, and you can solve for the metric, you get this. It uses the Weil-Majumdar relation. This is Sudhanshu Datta Majumdar, and it has closed time-like curves, but has no energy condition violation, and it is projected as the gravitational analog of the Landau levels. So this is called the Shom-Raychaudhuri spacetime. Okay, so that is roughly the end of the talk. Let me show you some photographs. This is AKR in his early years. Then that is AKR in his later years. This is AKR with his wife and with his children in Maryland University, where he visited in 1964. This is AKR with Naresh Dadich and Jose Senovilla in 1995. Fortunately, I was also there in this conference, so I heard him speak on his equation. Dieter Brill actually gave a very nice talk, if I remember. This is AKR with Shyamol Sengupta, Professor Shyamol Sengupta in Presidency College. And this is Sri Gujjar's drawing about AKR, Vishweswara. Okay, let me end by what AKR says in his diary of 2002. This is what he writes at the end of his diary. So how long will humans remember me or my work? My students may reminisce once in a while. Let us assume that will go on for 30 years. And given the present scenario of the scientific establishment, it is fair to say that perhaps for 10 to 20 years or so, a maximum of 50 years, my work will have a place in scientific discussions. After that, my work will possibly have no relevance or place in science. However, these speculations are in my view. So let us see. Thank you.
So I have time for some questions. Yes, Partha. Comment, Partha.
Just to comment on this last remark, see, this is already the 70th year, right? of the writing of the Raychaudhuri equation.
Yeah.
And the fact that we're still discussing it and using it, as you cited so many examples, means that he's wrong in this, right?
No, the diary was published, diary was written in 2002. So let's wait for 2072. So any more question or comment?
Yes.
Sir, when you have tried to derive the question,
Yeah, take a mic. Yeah.
yeah. Hello. When in the second page we have tried to derive the equation, so we have taken the Ricci tensor. So there is a part you have tell this V. In cosmological sequence, this is the if the metric is the anisotropic, then it is the volume scale factor like things.
Yes.
Okay.
In the isotropic cosmology, this V is A cubed, so it is the V dot by V is 3 A dot by A, which is the expansion.
Yes. Okay. So it is the acceleration equation, right?
Exactly. Yeah.
Thank you.
So I'm working on wormholes for my PhD research. So for wormholes, we will be doing some energy conditions, null energy conditions. Are they the result of the time-like convergence condition from Raychaudhuri equation, sir?
Yeah, in some sense, yeah.
So this condition, is it a hard limit? Because we'll be looking at something called exotic matter. So is such a matter possible, or is it prohibited by this equation?
No, you translate the convergence condition to an energy condition, and then it can happen that energy condition is satisfied over a certain domain of space-time, not the entire domain. Okay. But the requirement in the theorem says that it has to be satisfied over the entire domain.
Okay.
Okay.
Thank you, sir.
Sir, in one of the slides you told that Raychaudhuri equations is the generalization of Newton's work. Can you just give more reference about this?
No reference. It's very simple. Suppose you take a collection of free particles, okay, and now you're going to fix delta u, delta x. Delta x is the different positions and delta u is the difference of velocities. So delta u by delta x, if you fix initially, and you ask the question, what will happen to this family of particles? Three things can happen. They will either converge, or they will diverge, or they will stay parallel. In your Newton's first law, what do you say? You say if there are no forces, then the particle can either stay put, or it can move at a uniform velocity. Here, if you are looking at a set of particles with a given expansion to start with, then the consequence is that either they will move parallelly, or they will converge, or they will move away from each other. The next part is, if you want to find out what will happen if there are forces, then it's the gradient of the force which will dictate the behavior of the gradient of the velocity. That is the second law. Okay. It comes from the equation d theta dt plus theta square equal to del f del x. Del f del x is the way the force changes, that dictates the way the gradient of the velocity changes. Just as in Newton's second law, you say the force F equal to ma, here you say the gradient of the force dictates the gradient of the velocity. Okay. That's the sense it is a generalization of Newton's law.
So any other question or comment? So, okay, so if there is no more, so let's thank Sayan once again for the nice opening talk of this conference.